We are going to continue on this example where in the previous video we found the voltage across this inductor. There's a 4 millihenry inductor, and for this video I would like to find the instantaneous power and the average power during the 6 millisecond time span that we are given here. Know that the voltage across an inductor is L, the inductor value, times the rate of change of current respect to t. So we differentiate the current L di dt, and we have the voltage VL of t given as a piecewise function here. So this was from the previous video, right? So from the previous video, okay, so what we wanted to do here is to answer question 2 when we are asked to find the instantaneous power. So an inductor is which is a passive component. So the current I of t and the voltage across the inductor VL of t. So we know that VL of t is L di dt. So here we wanted to find the instantaneous power. So P of t, which is I of t times V of t. When we use the passive sign convention, the current is flowing from plus to minus, right? So from plus to minus, and the current is flowing that way. So then we have plus I times V. So when we multiply this piecewise function, then what do we get? We have P of t that is equal to, now for t less than or equal to 0 millisecond, we have 0 because the current is 0 and the voltage is 0. And then for 0 millisecond, 0 less than or equal to t less than or equal to 1 millisecond. So we're going to take this multiplied by this. Okay, so that gives me 20 times 5, 10 to the 3. So 20 times 5 is 100. So it's 10 to the 5 t. And for 1 millisecond less than or equal to t less than or equal to 2 milliseconds, we are going to take this multiply by 5, and that gives me 0. 0 times 5 is 0. Okay, so the power is 0. And then now from 2 milliseconds to 4 milliseconds, so what do we have? We have negative 20 that multiplies negative 5, 10 to the 3 t plus 15. Okay, so when we multiply this, we have 20 times 5, 10 to the 3, which is 10 to the 5. So 10 to the 5 t, 10 to the 5 t minus 15 times 20, which is 300. Okay, and then the next one is from 4 milliseconds less than equal to t less than equal to 5 milliseconds. So we have -5 times 0, so which is also 0. And then now from 5 milliseconds to 6 milliseconds. So what do we have? We have 20 that multiplies 5 10 to the 3t minus 30. So that gives me so this was 0, and then from 5, so 20 times, which is 10 to the 5t, and then 20 times 30, which is minus 600. Excuse me. So that's the instantaneous power. So we can sketch it. So when I sketch the power, so let me sketch it down here. T here, T obviously in millisecond. So I have 1, 2, 3, 4, 5, 6. So is a t equal to 1 millisecond, then it's a 10 to the 5. So let's say it's this. It's a straight line. So what is this value? Okay, so it's 10 to the 5 times 1 millisecond. So 10 to the -3, so that's 100. So this point is 100. And the slope is 10 to the 5. Okay, so then a t, and then it drops down to, let me see, this is not sketched properly, so there. Okay, so then it becomes 0 between 1 and 2, and then is between 2 and 4, between 2 and 4, right? 2 and 4. So it's a straight line. So when I plug in 2 milliseconds, it gives me 10 to the 5 times 2, 10 to the -3. So that gives me 200. So minus 300, that is minus 100. So this is minus 100. So then at 2, I am at minus 100. Then when t equal to 4, then it will be 400 minus 300. That is 100. So that will be this. Okay, so then when I sketch it, sort of looks like this. Okay, so that is and this is 100. And then now between 4 and 5 is 0, and then between 5 and 6, so when I 5 multiply 10 to the 5 times 5 milliseconds, so that gives me 500. 500 minus 600, that gives me minus 100. So at this point is minus 100. Then at 600, 6 millisecond, so 10 to the 5 times 6, 10 to the negative 3, that gives me 600 minus 600, that's 0. So we have 0. So this graph looks like this, right? So that's the sketch of the instantaneous power. Okay, so the instantaneous power, P of t in watt. So P of t expressed in watt is this. Then that 0, then this, then straight line, and 0, then 0, and a straight line, then a 0 after 6. So that is P of t. Now the third question was to find the average power. So the P average, right, which is the over this time interval, so 1 over 6 millisecond, integral from 0 to 6 millisecond of P of t dt. Right, so we're asked to find the average. Okay, so if you like, we could do is 1 over 6 millisecond. So integral from 0 to 1 millisecond, P of t dt, plus from 1 to 2 is 0, then it's from 2 millisecond, 3 millisecond, P of t dt, plus integral from 2, it's 2 to 4 millisecond, and then from 4 to 5 is 0, then now from 5 millisecond to 6 millisecond of P of t dt. So technically what we're asked to do is to find the area under this function. Right, so instead of performing the integrals, right, we are going to find this this area, the area under these triangles, and then we could just add them up. Okay, so I call this number 1, call this 2, I call this 3, and I call this 4. So as I was saying, this 1, this is 2, this is 3, and this is 4. So for number 1, I have 50 watt divided by 6, if you like. Okay, and then plus, because the millisecond cancel out with the millisecond, so I have 50 watt. It's 1 millisecond divided by 6 millisecond, so I cancel them out. So I have 50 divided by 6. Okay, 60 divided by 6 plus the integral from, so if you like, we can break it up into 2. So that interval, which is going to be negative 50 divided by 6 as well, right? And number 3, which is plus 50 divided by 6, and the last one is minus 50 divided by 6, so it's 0. So the average power here is 0 watts. Okay, so well, let's make sense of this this result. So the inductor, right, will store energy, right, during the first cycle, right, the first half cycle, so from 0 to 3, and then it's gonna release it back from 3 to 6. So that means overall the average power consumed by this inductor is 0. Okay, so this result reflects the fact that the inductor does not dissipate power. Okay, so instead it stores energy during this, for example, this 3 millisecond, and then the second half, which is the other 3 millisecond to 6 millisecond, release it during that time, and resulting to no net energy consumption over this time period. So this led me into this well-known property of inductor. So let's say we have a sine wave, and then let's say that we apply that as a current. So this is a current source, right? So this is I of t, and the voltage across the inductor VL of t. So the power, the instantaneous power, which is I of t, V of t, but we know that VL, right, VL, which is L dI dt. So if the current is a sinusoid, so let's say the current is given by this by a sine wave, so over one cycle. So let's say we have this, right? So that's a full cycle. So now let's say that this is the amplitude, so I call it the I max, right? So minus I max. So we could write the current I of t as Im, okay, sine omega t, for example. So the voltage in this case, VL, which is L d over dt of I sine omega t. So max. So when you differentiate sine, so I'll always make this a little circle to remind myself not to make sign errors. So we have sine here, cosine here, negative sine here, and negative cosine here. Okay, so when I differentiate, I move this way when I differentiate, right? But then I move counterclockwise when I integrate. So when I differentiate sine, I'll get cosine. So it's L Im omega cosine omega t, right? So that's VL. So then the power, the instantaneous power, which is L max square, okay, omega sine omega t cosine omega t, which is IV, so I of t v of t. Okay, so then what happens is that if I wanted to find the average power, P, the average, just use that notation. So I call this the time period, right? The full cycle. So then I have 1 over t integral from 0 to t, P of t dt. But I know that sine omega t, I know that times cosine omega t equal to half sine 2 omega t. Okay, so then when I have 1 over t integral from 0 to t of L Im square omega over 2 sine 2 omega t dt. So when I integrate this function, right, so 1 over t 2t, this is L Im omega, and then integral from 0 to t sine 2 omega t dt. So when I integrate the sine, okay, I'll get, I integrate sine, I'll get negative cosine, right? So L Im omega, square missing there, 2t. So I have minus 1 over 2 omega cosine 2 omega t from 0 to t. Okay, so that Lim square omega over 2t. Alright, so the omega cancels out, then this becomes 4, and I put the minus in front of it, and this gives me cosine 2 omega t minus cosine 0. Okay, so we know that this function is periodic, right? So omega is 2 pi over t. So then 2 omega t, right? 2 omega t equal 4 pi. Okay, so that means I have cosine 4 pi here minus cosine 0. So that is 1 minus 1. So this whole thing is 0. So the average power for this inductor, purely inductor, is 0. So in conclusion, the average power, okay, the average power consumed by an inductor is in a circuit, in a circuit with a sinusoidal current, okay, over one complete cycle, okay, 0. Okay, so that's what I wanted to highlight with this example. Okay, so this result, right, this result reflect the fact that the inductor does not dissipate power. Okay, so instead what it does is instead it stores energy during 1/2 cycle. Store energy one 1/2 cycle. Okay, and then release it during the other half cycle, and then release it during the other half cycle. Okay, so look, so then this leading to no net energy consumption over one full cycle. So over one full cycle. Okay, so I just really wanted to emphasize on this because when we talk about resonance later on, you know, this all this will make more sense to you. Okay, so I know the video is getting too long, so I'm gonna stop right there. So I'm gonna continue with another example in the next video. So in the next video, so please stay connected. So in the next video, I'm going to do an example where the load is not purely inductive, when the load is just a device that consumes another passive device, but it's not purely inductive. So then we are going to calculate an average power and total energy and all that, which is not going to be zero because it's not, the load is not going to be an inductor. So I feel like I need to do another example when the load is now purely inductive.